monitoring Bitcoin P2P network attacks and anomalies with eBPF and USDT tracepoints. Hi, I'm ZivXBTC and I contribute full-time to open source Bitcoin projects. One of these projects is Bitcoin Core, the most widely used implementation of the Bitcoin protocol. The software powers the network with a market cap of more than $1 trillion. This is roughly equal to the market cap of Meta. Bitcoin Core development has a strong focus on security and doing proper software engineering, as problems can hurt the network and bugs can cause users to lose their money. This includes extensive review of pull requests, good unit, functional and fast test coverage, along with test networks and simulation tools. But this doesn't reduce the need for monitoring of development builds, release candidates, and production deployments. The most important part to monitor is the P2P networking functionality. The Bitcoin P2P network is a distributed system consisting of tens of thousands of nodes, gossiping transactions, blocks, and IP addresses of other nodes. As the network is open and everybody, good or bad, can connect to the nodes, monitoring the behavior of the software in a potentially adversarial context is important. Attacks we are looking for are, for example, denial of service attacks, which either take up system resources or in the worst case crash the node, as well as privacy attacks or eclipse attacks. Motivated by anomalies previously only observed by coincidence, we spun up a few honeypot nodes. These nodes run different software versions, development builds, pre-releases, releases, and all have different configurations applied. The goals here are twofold. First, being able to analyze attacks, anomalies, bugs when they happen, and secondly, being able to feed the data, insights, and learnings back into development. To look into the software behavior during runtime, I've opted for tracing with eBPF and static tracepoints. Static tracepoints, compared to dynamic tracing with, for example, uprobes, allows us to have a semi-stable API even if the code is being refactored across versions. There are, for example, tracepoints for opened, closed, and evicted connections, as well as for inbound and outbound messages. These are implemented using the systemtap-probe macros. The tracepoint interface is tested in the CI with the Python frontend for BCC, and there are BPF trace and BCC example tracing scripts. The snippet shows the tracepoint for inbound P2P messages. 6 arguments are passed to the tracepoint with information about the peer which sent the message and the information on the message and the default message payload. The actual eBPF code for the monitoring lives outside of the Bitcoin Core project, the peer observer project. Specifically, the extractor tool written in Rust uses libbpf-rs to interact with eBPF. The eBPF program is written in C, and libbpf cargo is used to generate the Rust bindings for the functions and maps in the eBPF program. The T-structs that we pass around are read with the read underline function from the Rust standard library into the Rust struct counterpart. Alright, as an example of how this works, in user space, the Bitcoin Core node receives an inbound P2P message from a peer, and the message is processed in the process messages function. In this function, there is also the inbound message tracepoint. The tracepoint is reached, and the tracepoint arguments contain the information about the peer and the message we received. The function handling that message inbound from our eBPF program is hooked up to the inbound message tracepoint. This means once the tracepoint is reached, the function is called in the eBPF virtual machine in kernel space, and the tracepoint arguments are passed into this function. We reserve a P2P message struct in the ring buffer and fill in the tracepoint arguments. Using reserve submit here has the neat side effect that our struct is not on the eBPF virtual machine stack, but already on the ring buffer, and thus can be larger than the 512 byte stack size limit of the virtual machine. The payloads of Bitcoin P2P messages that we pass along with the tracepoints and want to have in user space are frequently larger than the 512 byte stack size. Once a struct is submitted to the ring buffer, the last 2 steps happen in user space again. The extractor reads the C struct from the ring buffer and converts it into a Rust struct. The Rust struct is then forwarded to our tooling and is, for example, used to generate metrics and in our anomaly detection. This allows us, for example, to visualize the messages being exchanged between a node and its peers in real time, which is a good demonstration showing the throughput of the tracing. At the same time, we can also derive time series metrics from the events and show them in Grafana dashboards. Some of these metrics are used for anomaly detection and automatic alerting. To wrap up, here are my closing thoughts on tracing Bitcoin Core with eBPF and USDT tracepoints. The combination of eBPF and tracepoints certainly fulfills the requirements for a real-time stream of events from Bitcoin Core. It gives us detailed insights into what was previously mostly hidden in a black box, and it's good to have a machine-to-machine interface as compared to logging, for example, which is more a human-to-machine interface. For our implementation, we made sure that preparing the tracepoint arguments isn't expensive, like serialization or hashing, and we don't place them in tight loops. Similar for gating the tracepoints, that means only preparing the tracepoint arguments when someone is actually hooking into them eliminates all runtime overhead when nobody is using them. We have an open pull request for this. The eBPF side and the ring buffers seem to be quite performant for our use case. Inserting new tracepoints has a minimal code signature of only adding a few lines consisting of the tracepoint macro. Most of the code added along with tracepoints are the interface tests for them. One obvious limitation is that our eBPF tooling only works in Linux, and we can't use it to monitor on macOS or Windows. I have experimented with reusing our tracepoint macros for dtrace probes on macOS and FreeBSD. This would allow tracing on these platforms too. We've also faced problems with testing the tracepoints in CI. This ranges from problems with the Ubuntu BCC package not being up to date or broken, to our CI running in containers which might have a different kernel from the host system, which led to problems. And looking at the process in general, extracting events from a user-space C++ process via an eBPF program in a kernel written in C to a user-space program in Rust or Python could be seen as a detour via the kernel, especially with the permissions required for BPF calls. Advising people to run random tracing scripts downloaded from the internet as root might also not be the best idea. All in all, eBPF and USDT tracepoints gets the job done. Well done, I would say. But it might require you to jump through a few hoops on the way there. Alright, thanks for joining. I will be around in the Slack channel for the Q&A.